everyone. So my name is Łukasz Kaczmarczyk, and we will show you some in fast way how you can solve the PDEs using MoFEM, and I will focus on the design and sustainable code development. So I will start with the school program for this part. I will give an introduction about code design, heterogeneous and hierarchical basis, what are the pipelines, the general idea of them, and why we're using them. Honk will tell you about user data operators and simple interface. And we will present you how you can use that ideas to solve Poisson problem. Then we'll look at the linear acoustics and how to approximate complex variables, forms integrators. And finally, Carol will tell about the elasticity and how you can implement the code which works simultaneously both in 2D and 3D case, and how you can then the same code easily without the effort expand to the large strings, so that you don't waste the effort of implementing 3 codes at once. You have one code which works and you can test it quickly. And last talk will be from Andre, and he will tell you about the mixed formulation, HDIF and H-car spaces, error estimation, and the p-adaptivity. So we will have a summary at the end. Before I will try to convince you to MoFEM and the ways how we do the things, I want to encourage you to look not necessarily into the MoFEM, into contribute to open finite element community. And there is many other codes than MoFEM which are on the market, and why you should join one of them, not necessarily us. So first thing is that for most cases, when you look, the code is written by PhD students. Sometimes it's written by postdocs, less often by professors, but the professors really know how to write the code. So typically, research software is written by inexperienced people which learn how to do that. But once they know, they have no time to do it. So, and no many research codes live because of that beyond the PhD, because when people will move to some other place, development is discontinued. And in few years' time, we don't know how to run it. So such code is not sustainable. We have a problem with the track record of the code itself. We write the papers, but the code has no track record, and there is no pathway how you can use that code in the industry. And industry, that's why is bound to use the commercial codes, not the research codes. So you have to break somehow that barrier. And finite element code is complex. And in fact, if you want to do it really well, it takes many PhDs in the sense that it takes many years, longer span of time than the single PhD. You're doing that for decades. In fact, if you look at the serious codes, they are developed for 20, 30 years and more. So successful open research code are developed by the community, so that the programming is not isolated work. It's a big social aspect of it. And you have to engage the community, and then you're building a very complex structure if many people contributing with the various sets of the skills. So that's what is offered to you by when you join some finite element community, not develop it in isolation or small group. So we created MoFEM initially in the Glasgow Computational Engineering Center. And you can go to the MoFEM webpage, MoFEM GLA AC UK, to see how it looks like. You will find out there are tutorials. Some of those tutorials which are on the webpage in the development section will be described later on. You can read about MoFEM in the JOS journal, and MoFEM is supplemented by a set of the different toolkits, or we call it then user modules, that they are developed separately for industrial or PhD needs, and they are not part of the MoFEM, and they have a different licensing depending on the needs. So then we have, for example, acoustic code. You have a submarine here, and topological optimization, bone remodeling, shells and plates, fracture mechanics, contact, and much more. So what is the code in the nutshell? So first of all, is the core library has 100,000 of lines, but it's developed by 20 contributors, maybe more. In fact, it's difficult to track, and it's developed for 8 years. So we are relatively young code. So it's time to join us and then build things together. If you will think about that code with the tests and the validation which we have to do it, for a single programmer working 5 days in the week, professional for programming, it will take us 64 years to do it. So this is large volume of the knowledge accumulated in it. It's mostly written in C++. I know that is a steep learning line, but you have a benefits from using C++. At the end, you have a speed and you have a great flexibility to do the things in the novel and the different way. It has 70 tutorials, and we are writing more. And we have tests which are run on Jenkins and submitted to CDASH. This is automatized process. License is GNU license to protect all developers. So what that means that no one will take your code and use it for own benefit. You have to agree for that, and GNU license protects you. So you can freely contribute without the worrying that someone will use your work without your permission. It works on Linux, Mac OS. When you have when you install Docker, you can run it in Linux, but as well you can run it as a cloud computing. So you can run it in the Jupyter Hub, Jupyter Notebooks. This is how we give it to the bigger public. What it offers? It offers heterogeneous and hierarchical arbitrary order approximation basis. I will explain later on what that means. It supports wide ranges of spaces from L2, H1, HCal, HDiv, so you can solve the solid mechanics problem, fluid mechanics, and electromagnetics if you like. So for example, this is around 300 lines of the code in MoFEM that you have a distributed mesh. It's coarse because we have high order approximation basis. You can solve the electromagnetic problem with the coil in the middle. And then at the end, you can run the particles in the cell when the charged particles are driven by the Lorentz force. Andrei will talk more about the HCal spaces, but you can see as well the tutorials max 1 and max 0 and max 1 for this problem, which you can see over here. Code support heterogeneous meshes, so we can mix triangles with quads, prism with the tetrahedrons. You have a great flexibility. There are data structures which handles different things. They handles multiple fields for coupled or mixed problems, multiple subdomains. You can mix formulations. You can do mixed formulations. You can integrate of the skeleton. Data structures handles that. Easy to parallelize. Every test which we show can be run on the parallel computer on the distributed memory. And code reading various formats from MET format used by Salome, our ADF, our industrial partner, Gmesh, Qubit, and so on. The key thing is that we take a big effort that you can easily transform the information about the boundary conditions from the mesh into the code. And much more, but we have no time to discuss that. What are the MoFEM origins? So we develop it to deal with the gas cool reactors, to model fracture of the gas cool reactors. And we do that because the commercial codes fail to do that. So somehow there is a big incentive to industry to search for alternative solutions. And MoFEM was selected from many codes in 2017 finally, and now is used in the practice by engineers in the EDF and Jacobs to solve the practical problems. They even write the whole interface around it, they call it graphite workbench. IGR reactors contribute around 15% to the energy production in the UK, and they are located, as you can see on that map. We are so successful that by creating a software, we created the impact case for REF 2021. So this is our recent achievement. It's, as I said, so in order to compete with the industry, we have to propose novel finite element technology. And a code is free and open. It's a research code, but we try to develop that code professionally. Okay, wait a second. So this problem about the fracture, why it's so complex? Because it's a multi-physics. We're dealing with radiation, deterioration of the material due to oxidation. We have more than 10 different approximation fields on problems like that, which approximate various things. We have a complex boundary conditions, contacts, spring elements through which crack has to propagate. We have a heterogeneous approximation spaces that in order to get the efficiency, we have to raise the approximation order near the crack tip. It's running in the parallel. It's topology evolving in the continuous way. And the biggest challenge, in fact, is that you're working in academia. What that mean? That the people are coming and going. This is not like in industrial development of code that you have a set of the same people which working together for a long time. There are postdocs which finish their postdoc and they going somewhere else. They getting a lectureship position. So then you develop the code over in time and space. So your code itself has to be designed in such a way that allow to accumulate knowledge and transfer the knowledge from one generation to another. And it has to satisfy at the end standards of the nuclear industry. Okay, so what is the special thing about the MoFEM design? It's that we appreciate the fact that the real life industrial problems are complex, like a space shuttle. So we have to find a way how we can take any complex problem and decompose that into many simple tasks. And each part can be tested independently. It can be tested by various people, PhD student, written by the PhD student, postdoc, or whatever, human resources professor, and then when you have that, you have to find code have to allow you to divide the work into the groups, and then it has to allow you to put everything back efficiently, that everything works at the end. So what is the special? So then we divide we created the special tools in MoFEM, like pipelines, which I will focus on that, but there are other things which allow you to do that thing. Develop the research code for industry with the complexities of the working in the academia. So every finite element program, what every finite element program needs, it needs something which reading the meshes, something which create the approximation basis on the finite elements itself with the operators, differential operators on them, integration rules, linear algebra, and the solvers, linear, time solver, nonlinear solvers, eigensolvers, and some optimization tools sometimes, depending what you want to do. So, of course, we don't develop everything from scratch. We have this, we have this software ecosystem. And this software ecosystem is based on 3 legs for stability. First thing is MOAB, is which this is library, which manage the topology, and through that library we can read the various formats, and then you can do very complex operation on the mesh and manage data on the mesh itself, block sets, side sets to manage boundary conditions. We have a PETC which manage algebra for us on the distributed processors and the solvers, and in the middle of that is a MoFEM, which transfer the information from topology into the system of the algebraic equations, which you potentially solve in the sequential way. There are other things like mfront. This is the library which is set of the different material models. ftensor, which allow us to do a very fast calculations with the tensors from second, third, fourth order tensors, explore the symmetry of those tensors. We modified that library for the needs of the MoFEM, and everything is managed. This complex ecosystem is installed by SPAC. This is packaging managing system, which take care about how to install that in the simplest possible way. What is the structure? So typically you start with the physical model. We working with the ROM in the continuum mechanics. Then when we have a mechanical model, because it's continuum mechanics, is lead to the partial differential equations, system of the partial differential equations. So we have a mathematical model. Typically, those equations we cannot solve. There is no analytical solution because there are non-linearities and other features. So then we use the discretization techniques, numerical methods for do that. And then again, there are three blocks in the core library. We have a core library which has those three blocks, three legs: MOAP, MoFEM, and PETC. And user just using the interface, wrapped interface to read the mesh, add the fields as many, set up the program, create the finite element, implement user data operator. You will see what that is later on. Solve the problem and post-process results. And this is user module. It could be a separate repository. So I will explain what this is. Coriolis law, and then imagine that you have a solid shell element, and you can estimate a posteriori error. So when you solve the problem, you can see these concentrated red regions. This is the point where error is high. So what we can do, we can adapt the mesh. We can rise the, for example, we can make mesh denser. We already did that near the holes because there is a perforated plate, but we can rise the approximation order. So you have a heterogeneity of the approximation order. Some elements has order 8. Some of our elements are order 2. When you rise this approximation order in the smart way, you can achieve so-called exponential convergence. So we can get the optimal solution, desired solution with desired error with the minimal computer effort. So when you do that, you have a kind of the uniform approximation error. So this is, you can see that this is a logarithmic scale, so the error is more or less uniform and small. There is no concentrated zones where the error is not necessarily a good one. Andrei will tell you how you can write the error estimator and how you can do API adaptivity later on. So we have a heterogeneous, each entity can have a different approximation order. Entity, we mean that edge, face, volume, and so on. And it's hierarchical. What hierarchical means that you can group the base functions by the order. You have a group of functions which are first order, second, third, and so on. So typically Lagrange shape functions, you cannot do that. You have to introduce the nodes, and you can see each time you increasing the approximation orders, all the shape functions are changing. So the making approximation, which is the heterogeneous, is possible, but very tedious and hard to do that. When you have a hierarchical base, you add the functions and they are grouped by the approximation order. In 2D, for example, it will look like on the figure below, when we have you can see that we have some base functions associated with nodes, edges, and faces at the end. About that, you can read in the tutorial 2, Fundamentals 2, and follow that link. So, but we have, in fact, in MoFEM, we are not only restricted to the hierarchical basis, we using Bernstein-Brezzi polynomials as well for fast integration. So we grouping the entities first by the type of the entity. So we have finite element, triangle, for example, here, and we decompose it on the sub-entities. And on each entity, we have a hierarchy of the approximations. Why are we doing that? Because then we can group the base functions by the entity, vertex, edge, face, and volume in case of 3D. So, so every finite element, in fact, can be decomposed on the sub-entities like quad, triangle, hex, or any other shape, prism, and so on. So what that mean? That means that, for example, I have this bunny, like we have seen it before. I decompose the element, and then on every element, I can run the set of the so-called user data operators, for example, to calculate the thermal problem. So what I mean that, in fact, for me, it's not longer important what is the shape of the element. It's important how many edges element has, how many nodes, and how many faces it has, and volume finally, and then I will run the so-called user data operator for each of those. How to solve this is the case for a thermal, that I have a finite element to calculate the right-hand side, finite element to calculate left-hand side, and then this heat type of the problem, you can use the heat method to calculate the geodetics on the surface of the bunny, and then see tutorial scalar 9 if you want to see how to calculate the geodetics on the surface. So what are those? So this thing, we call it pipeline, that you set have a set of the different operators which you run on the entities. So why are we doing that? Because now when we implement the operator for a sub-entity, and what that means, that no longer shape of the element matters. You have one implementation which works for quads and triangles, or tets or hexes. It's independent of the approximation base. You can switch the approximation with the flip of the finger and use the Legendre, Jacobi, Lobato, Bernstein basis if you like. That basis which suits your needs the best. You can raise the approximation order because you're raising it by the entity. You can write the code that is independent on the dimensions. Carol will talk about that. And then at the end, you have those operators which have every complex task is split on simple operations. And then, for example, Carol can, or some group of people can implement the elasticity, another group of people can implement contact, and they put the operators in the pipeline, and suddenly you have mechanical problem with the contact. Each parts can be tested independently. And we have example like that. There are tutorials when we implement the elasticity, separately contact, and we put the things together in order to drop the bunny, elastic bunny from some height. Okay, this is what I want to tell you about that part. And if you have more questions, you can ask them over here. You can as well go to the Google Groups over that link. You can ask the questions there. But I will pass the baton now to the Hong when he will tell you, start with something simple about the Poisson problem, and he will focus his attention on user data operator, what it is and how to implement that. Later, Ignatius will tell you that you don't have to even implement that. But so then I pass the baton to now to Hong.
Okay,
sorry,
yeah.
Hong. Before you start, is there any question from the audience for Lukasz on this first part? No? Okay, then we leave the questions for later, and Hong, please.
Yeah, okay, yeah, thank you. Thank you for the introduction. My name is Hoang Nguyen from Northumbria University. So today, as Lukasz mentioned, I would like to show you the implementation in MoFEM, like just a brief about that, and the example that suits for the illustration would be the symbol Poisson problem. So here's the outline of my presentation. So first I will set out some goals of the presentation, then the theory of the Poisson problem. Then I will focus on the explanation of the different components of the implementation of the problem in MoFEM before showing you how to run the analysis and conclude with some summary. More detail of the theory and the implementation that I'm going to present here is provided in the tutorial SCL1 that you can find in the MoFEM webpage. So the goal of the presentation, as mentioned, I would like to show you the implementation of a simple Poisson problem in MoFEM, the code structures, two important concepts in MoFEM. They are pipelines and user data operators, of course, with the detail of the implementation. So I believe all of you here are familiar with Poisson equations. So it is used to model different physical phenomena, for example, steady state diffusion, heat flow, or electrostatics. So the strong form of the problem, you can see we have the divergence of the gradient over here of the field U that equal to the body force F on the domain omega over here, and here for the simplicity we consider the homogeneous boundary condition on the boundary d omega over here. So by multiplying both sides of the equation in the domain by a test function and then integrating by part, we arrive at the weak form you can see over here, where the test function delta u in the space H1 0. Then we have the field U is approximated by the linear combination of the safe function phi over here and the degree of freedom U bar. Then the global system is obtained, and you can see Ku equal to F, where K is the stiffness matrix, U is the vector of unknowns, degree of freedom, and F is the force vector. So I'm sure all of this one is very familiar for all of you. So these components of the element stiffness matrix and the force vector can be calculated using numerical integration, where you can see over here W is the integration weight and J is the Jacobian of the Jacobian of the transformation of the element between the parent and the global coordinates. We also have like a tutorial that you can refer to if you're interested about the numerical integration that you can find in the link here to the MoFEM webpage. So once we have all the equation derived, and we're now focusing on the implementation of the problem in MoFEM. So the primary function here, you can see the Gruen program function that will include some other function that execute a series of tasks. So we have read mesh that will read the mesh, set up the problem, boundary condition over here, responsible for setting up boundary condition and applying boundary condition as well. Assemble a system function. It's responsible for assembling the system equation. We set then the function for the set integration rules. Then the function for solving the system of the equations, and then the processing is done in this function of output results. So now I will be focusing on the first function, the readMap function over here. The first one that this function do is to get the symbol interface that provide the functionality for the fast and straightforward implementation in MoFEM. There are other interfaces for more complex problem, but for simplicity of the current problem and the limit of time, I will focus on just the symbol interface only. The function over here, get options, and the load files that are responsible to get the file names and load the file to the program. And over here, if, you can notice that we have the error handling. It is suggested by the keywords over here, MoFEM function begin and MoFEM function return 0 at the bottom. So this error handling in each of the equation in each of the function in MoFEM that would help user or developer quickly identify where the error come from if there is one during the compilation or the running of the analysis. The second function is the function for setting up the problem. So in this function, first we add the domain field, and in this domain field we have the name of the field, so we name it domain field over here. We have this space of the approximation, we use H1 for the scalar space. And here we have the base function. So in this case, we use the Bernstein-Bezier base as Lucas introduced. For the coefficient 1 over here, it's representing the number of coefficient per shape function. And here we have the scalar problem, so it is 1. It should be noted that here we just add the field to the domain only without the field for the boundary, as we use a homogeneous boundary condition for this problem, so no need to add the field to the boundary. But of course, if you use non-homogeneous boundary condition, then we need to add the field to that. Next one, regarding the field order approximation. So in the code over here, you can see default will be third order, but of course, user later, they have the option to indicate arbitrary order that they use by the command line options dash order over here. And finally, we do some like function to set up the problem. The next function is about the boundary condition. So two main things happen in this function. The first one is to add the entities where the boundary condition is applied, and then second one is to apply the homogeneous boundary condition to the block set of the entities. So in the first part, so we take all the edges that name boundary condition, for example, for this mesh. So we name that in the name the block set in the mesh, and then the code would take all the entities that associate with that block set, and then we add to that block set all the vertices that are adjacent to the edges that we get previously. Here you can see MoFEM wrap, the functionality developed in MoApp library, and MoApp is the part of the Sigma library that developed by researcher at Argonne National Laboratory. For the second part of this function, we can see here we apply the homogeneous boundary conditions by removing all of the degree of freedoms that are associated with the block set defined above. For the assembly, this function is responsible for assembling the system. So here we introduce two important concepts in MoFEM. The first one is the user data operators, and the second one is the pipelines. So user data operators are where we implement functionality needed to calculate the left-hand side matrix and right-hand side vector. And the pipelines is where we push the develop user data operator to, and it will be used and executed throughout the program. So in particular, for this Poisson problem, we have two pipelines. So the first pipeline, you can see left-hand side pipeline over here is responsible for the calculation of the left-hand side, and the second one here responsible for the calculation of the right-hand side. And these two pipelines are managed by the pipeline manager over here. You can see in the code. Regarding the user data operators, we have operators to calculate the inverse Jacobian and the left-hand side matrix. These are two operators that will be pushed to the left-hand side pipelines. And the other operators here that are responsible to calculate the right-hand side vector will be pushed to the right-hand side pipelines as expected. Now we focus a little bit more on the detail what is doing here in the code in the user data operator and the pipelines. So for the operator that calculate the inverse Jacobian, and so the first one is responsible to calculate the inverse Jacobian. You can see over here of the transformation between the parent coordinates psi and the global coordinate x over here, and then it will be used to calculate the gradient of the shape function. So once we have these operators, then actually it's like the operator that already developed in MoFEM, and we just use these operators. And once we have these operators, we just push it to the left-hand side pipeline, as I mentioned in the previous slide. The next operators that will be pushed to the left-hand side pipeline is the operator that calculate and assemble the element stiffness matrix. So you can see over here, we loop over the integration points as expected in any other finite element program. And then in that loop, we have two nested loops that loop over the row and the column data to calculate the element stiffness matrix according to the formula you can see over here on the left-hand side. After each loop, the data for the base functions and the integrating weight will be shifted to the next one. You can see over here. I think it should be mentioned here that we use the F-tensor library that use the Einstein notation. And you can see here the index I is a special variable that enable the summation. So the next one for the right-hand side pipelines, similarly, we have the user data operators that's responsible for the calculation of the right-hand side vector implemented here in the same manner in the previous slides, and then that will be pushed to the right-hand side pipelines. Here, I just want to also mention that the code for the left-hand side and the right-hand side that we see in these slides are just the definition step of the pipelines and the user data operators. All of the actual calculations will not be executed here, but in the function of the source system, which we will show later. So basically, this one is just the definition and no calculation when we run the code. The next function is the one for setting integration rules. So you can see over here, we can set the integration rules that we would like to use for the left-hand side and the right-hand side separately. As we are able to set the different integration rules for different operators separately, then there is a potential to save computational effort in case the functions that need to be approximated have different polynomial orders. The next functions over here is the solve system function. So here's the place where the system of equation is solved. In this function, I would like to focus on two things. The first one is the discrete manager, and the second one is the KSP solve. So the discrete manager is the PESI entity, and PESI is the library for scientific computation developed by researcher at Argonne National Laboratory. And this discrete manager asks MoFEM to give it a matrix and vector, and then MoFEM would call the pipelines for the left-hand side and the right-hand side, and execute all the user data operators that has been implemented, and then provide it back to the discrete manager. For solving the system of equation, here we use the KSP solver, also provided by PESI. And this function, KSP solver over here, is where all the loops and the calculation take place. The loop over the element and entities also happen here. So as you can see, MoFEM is tightly integrated with PESI for solving system equations. So the last function that's responsible for the post-processing is the output results. So you can see here, first we clear the pipelines that we created, that we had before, and then we generate the reference mesh. We add the field we want to be outputting, and then we replace the right-hand side pipeline for processing. Then we look over the final elements to obtain the field value, and then finally we write the output in the H5M format. So the video over here show the process of developing and running analysis in MoFEM. So the code normally divided in CPP file, where we have the main function, and the HPP file, where we have the user data operators. So once the code is developed, we compile the code, for example, in the terminal. Once we have the binary file, we can run the analysis by specifying the input file name, the order, and then we use the MB convert to convert the output format to the VTK format that we can open in ParaView. You can see over here, and then we can use the filter in ParaView in order to visualize our result. Okay, so there are several possibility for extensions over here. So the code that I just showed you is for 2D problem, 2D Poisson problem. So with minimal effort, you can extend it to 3D by just changing just few lines of codes. It is also straightforward to extend the code to cover non-homogeneous boundary condition, or you can see over here, non-linear problem, for example, non-linear minimal surface equation. You can also extend it to cover the time-dependent problem. For example, here we have the time-dependent wave equations. The tutorial from SCL 1 to SCL 7 over here, we walk you through all of the implementations of the extensions that I mentioned. Even though there will be work to do with the text of the tutorial, but the codes are available for you to play with if you are interested. That led me to the summary of my part of the presentation. So I have shown you the general structure of the program developed in MoFEM, implementation of user data operators to calculate the left-hand side matrix and the right-hand side vector, then how to push it to the pipelines, and then running the analysis and some possible extension of the code. So I hope that you will find MoFEM interesting and consider to join the MoFEM community. Thank you for your attention.
Thank you. Long. Are there any questions for our speaker? Any curiosities about the code? No, at this stage. Maybe we can continue with the next presentation. Lukasz, what do you suggest?
Yeah. So the next will be Ignatius.
Hello. My presentation will, the duration of my presentation is about 20 minutes, if that is okay.
Yes, I think we can do that, and then we stop for the break.
Okay.
Yeah.
Thank you. Thank you very much. My name is Ignatios Athanasiadis, and I'm one of the main developers of MoFEM, and I'm a postdoc at the School of Engineering of the University of Glasgow in the GCEC group. And today I'm going to present you the third part of the present UKACM school topic on many flavors of weak forms. That is the topic of linear acoustics. So in the beginning of my talk, I'm going to discuss the goals of this presentation, and then the boundary value problem that's going to be solved in the present talk is going to be described, and the strong and weak form equations that govern this problem under consideration are going to be briefly discussed. Then the code that has been implemented in MoFEM to solve the linear acoustics problem is going to be dissected, and finally post-processing of results and the results themselves are going to be discussed. So the goal of this presentation is to understand how to solve complex field problems, how to deal with two fields in MoFEM, and also maybe the most important bit is to how to push forms integrators in pipelines. That is an important concept both for current users and developers of the code and for future ones, because they can develop and solve linear problems in an easy way and very fast. Everything that will be presented in this talk can be found in the tutorial CLX in MoFEM web pages. So the 2D problem under consideration in this presentation is going to be the transducer generator. And here you can see the geometry of this, where each edge is one unit length. And with gray color, you can see the area that is going to be our domain that is denoted by omega. The red lines presented here are the quasi-absorbing boundaries that are denoted with gamma 1, and with black line is denoted the location of the transducer generator. So it's the boundary where the source is applied that is denoted by gamma 2. Now let's go to the strong form of the equations that govern this boundary value problem. It's the wave equation that you can see here that is true in the whole domain of our geometry. And this equation involves the wave speed that is denoted by c, the pressure field that is denoted by capital P, and time that is denoted by t. And this is a hyperbolic equation that involves second derivatives in time and space. Regarding the quasi-absorbing boundary conditions, the equation presented here, that is the Bayes-Turkel boundary conditions, is taken into account, and it's true in all the boundary gamma 1 that is presented with a red line. Capital N is the unit normal vector on gamma 1. Also, Dirichlet boundary conditions are taken into account, and they are true on boundary gamma 2. And this is a monochromatic cosinus function of amplitude equal to 1, where with omega frequency is denoted. By assuming that the solution of this system of equations admit separation of variables, we can try to find for the solution of the pressure wave to be equal to the real part of this product here, where the right-hand part is the complex wave, and the left-hand part is a variable that varies only spatially, and we assume to be complex field with two independent variables, that is the real part and the imaginary part. So when we do this assumption, we can substitute this product into our equations, and we can find that the components of time, since this problem is monochromatic, the components of time can be eliminated, and we end up with equations that involve complex values only. And as you can see later, in order to take the weak formulation, we first take into account the new problem that has been recovered after that substitution, that is the Helmholtz problem. And as I said before, we end up with a complex value that is equal to 0, but because the real part and the imaginary part have to be simultaneously be equal to 0, we can split the two parts into two equations. And here you can see the first row of the equations being the real part of the equality that we recovered, and the second one being the imaginary part. And these two are simultaneously true in the domain omega. Then for the quasi-absorbing boundaries, these two equations will be simultaneously true on gamma 1. And in order to take into account the source, these equations will be true on gamma 2. So in these equations, a new variable is presented, k, that is the ratio of frequency over time speed. And again, as I said, P is the spatially varying pressure that is a complex field. And now once we end up with our weak form, we want to find functions for the real part and the imaginary part that are in H1 functional space. And once this is done, I would like to say that K is the so-called wave number, that is the number of waves per unit length. So that's the physical meaning of this parameter. So to end up to the discrete form, we approximate these two fields with a linear combination of shape functions where they are both in the same space, but for the real part we take into account those that are denoted by phi, and for the imaginary part those that are denoted by psi. And by substituting this decomposition, we end up to this system of linear equations. This is a discrete system of equations. And on the left-hand side, we can see the bilinear forms, while the right-hand side is equal to 0. But on this, we have to impose also the essential boundary conditions that are fulfilled for these two equations in the integral sense. So again, similarly to the previous presentation that was done by Hong, a function that is called the run problem is the one that is calling for a series of other functions that deal with this problem. The first one being the read mesh that will read the input mesh. Then the function that is called setup problem is going to be invoked, and this involves definition of the fields within on the entities of our input file. Here, a simple interface gives us access to the domain elements, but also the boundary elements, because in this problem we need to access both domain and boundary. And then two fields are assigned for the domain and the boundary. One is for the real denoted by P real, and the other one for the imaginary field that is denoted by P imag. They are both in H1 space. The base that is chosen is Ainsworth-Bernstein Bezier base. And finally, the number of coefficients per shape function is equal to 1, that being that the fields are scalar. Also regarding the choice of order, similar to the previous tutorial, the command parameter dash order can be used in order to change the order to change the order by the user. Then regarding boundary conditions, this function is invoked, and within this, this deals properly with the boundaries gamma 1 and gamma 2 in order to be taken into account while assembling the system of linear equations. Moving forward to the assembled system function, this is the most important function for this tutorial because, as I said earlier, the focus will be on pushing forms integrators, and the main purpose of this is to push them into the proper pipelines in order to be then delivered by the solve system function in order to start going through them and computing and assembling. That is done in the next function. Here you can see that a pipeline manager is defined, and this pipeline manager is going to manage the various pipelines that are going to be used. K here is given by default equal to 90, but it can be changed by the command parameter -k. And the series of lambda functions in C++ can be seen here. And those that are of the most important are set domain and set boundary that are called in order to push domain operators and boundary operators in the pipelines. Here I would like to have to seize the opportunity to explain a little bit more what forms integrators are, because they are a very important concept, as I said. And they are a templatized class to calculate and assemble linear and bilinear forms. They are tested and optimized already, and therefore they offer ease, confidence, and rapidness to fully implement linear operators without a lot of time to be needed to be spent in order to have a running code. Back to the implementation of the function. Now we're going to have a closer look on set domain lambda function. In this lambda function, the pipeline that is going to be used is solely the domain left-hand side pipeline, because for the domain, only bilinear forms to the left-hand side are going to be assembled. And therefore, all operators presented here are going to be pushed to that pipeline. As Hoang said earlier, for 2D problems, we have to push the operators that in order to evaluate the inverse of the Jacobian and then transform the gradients of shape functions from the parent domain to the spatial domain. And now I'm going to focus on forms integrators. So the first operator that is pushed is op domain grad grad. And this is basically an alias for the template op grad grad that operates on domain elements and also acts on for scalar base scalar field in the 2D domain. Moreover, this operator, by giving these two strings and this function, it operates on real rows, real columns, and evaluates this integral. And also by passing this lambda function beta, this is passed by pointer and returns -1 in order to multiply this integral by -1. A similar operator, the same operator is pushed next, but now this operator operates on imaginary rows and imaginary columns. And the same lambda function is passed because it's multiplied by -1 and evaluates this integral here. After that, a new operator is pushed. This is called op domain mass, and this is an alias for this template specialization that again operates on domain elements, and it acts for scalar base and scalar field. This operator evaluates this integral here, and as I said before, by using these strings, it operates on real rows and real columns, and the lambda function k2 is passed by pointer in order because it returns the square of k in order to multiply this integral by the square of k. The same operator is pushed, later on with the same lambda parameter, but now this operates on imaginary rows and imaginary columns. Finally, these domain elements have to know what kind of integration rule they have to perform, and this is done by passing by pointer the integration rule lambda function in this function that gives access to the left-hand side domain elements. Now we move to the second very important lambda function here, that is the set boundary function. And in this one, we are going to do all assemblies that are related to degrees of freedom that are located on the boundaries of our input file. Two pipelines are considered here. The first one is for the left-hand side boundary, and the other one is for the right-hand side boundary. For the left-hand side pipeline, the first operator that is pushed is op boundary mass, and this is an alias for the template specialization op mass that now acts on edge elements and operates on scalar base and scalar field. This is pushed in order to evaluate this bilinear form, and now for the first time you can see how imaginary and real fields can be mixed. So this acts on imaginary rows and real columns in order to evaluate this integral here, and Kp now is passed as a pointer function in order to multiply this integral by k. Next, the same operator is pushed again to the same pipeline, but now this one operates on real rows and imaginary columns, and a different lambda function is passed in order to multiply this integral by minus k. Again, the same operator is pushed, but now this one is operating on real rows and real columns rather than having the a mixture of the two like before. In order to evaluate this integral presented here. Finally, for the right-hand side pipeline, one form integrator that evaluates a linear form is pushed, and this one is the op boundary source, and it's an alias for the templatized the template specialization op source that operates on scalar field and scalar base. And this is pushed in order to evaluate this integral and assemble this on the right-hand side of our system of equations. Also, this beta lambda function is passed in order to multiply this integral by -1. Finally, the integration rule, similar to before, has to be given to both right-hand side and left-hand side boundary elements. Also, here in the next steps, the solve system will be invoked in order to evaluate and assemble a series of the pipelines that where the operators presented before are pushed, and output results and check results functions are invoked that work similarly to what Huang showed previously. So next we go to the results. So 3 types of meshes were used: coarse, moderate, and fine, that are presented here. Initially, the influence of order of choice is investigated. So for all these results, analyses were performed for k equal to 180 and coarse mesh. And intensity that is given by the formula presented here is evaluated. So moving from left to right, the order is increasing from 1 to 4. And in the first 2 analyses, the result that is recovered is not really meaningful. But then as the order increases, the result is getting better and better, as you can see. Then the influence of the choice of k is investigated. And for all these analyses, an order of 8 was chosen for a coarse mesh. And again, intensity is presented here. So from left to right, k increases from 90 to 720. As you can see, as K increases, the focal point that is presented here with gray is getting shorter and narrower. And also the various waves that are presented here are getting higher in number. But for the case of K equal to 720, again, we don't get a meaningful solution. But this can be improved either by increasing the order or by making the mesh denser. And therefore, we choose to improve this solution by making the mesh denser. So from the left to right, we have denser and denser mesh. And we can see already by using the medium mesh how the results are improved. And for very fine one, we get excellent results here. Finally, we can, by post-processing, we can see how the wave that was evaluated by the solution can be seen how the way that it evolves in time by evaluating this linear combination for different time positions. So to summarize, the solution of the Helmholtz problem was presented for finite element approach. An example of how to treat two fields in MoFEM was described in detail, and also how to push forms integrators in pipelines. Finally, the influence of H and P refinement was presented. Thank you very much for your attention.